The story of US air dominance starts not with a new engine or a bigger budget, but with a new idea. For decades, the most advanced jets were complex, expensive, and trapped behind proprietary closed systems. That old way of building air power led to a fundamental weakness: systems that could not keep pace with changing threats. The world's security challenges evolve faster than traditional aircraft programs can update. Software changes that should take weeks often take years. This stagnation is exactly what the Beacon platform by Northrop Grumman was built to break. Beacon is not just another aircraft. It is a decisive platform engineered to accelerate innovation itself, leaving no doubt about the US commitment to control the skies. Beacon began with a simple choice: to design a next-generation multi-purpose jet that invites new technology rather than hiding it. This single difference changes everything about how missions are built, tested, and deployed, ensuring US and allied systems always hold the advantage. The foundation of Beacon's power is its autonomous testbed architecture. Most aircraft simply fly. Beacon teaches machines how to think. This is not guesswork. The jet pulls from more than 500,000 autonomous flight hours accumulated across Northrop Grumman programs, giving it a baseline of maturity few rivals can match. This vast experience ensures that new capabilities can be tested, proved, and deployed decisively. Instead of waiting years for new systems to be verified, Beacon compresses the entire timeline. Engineers can plug in fresh autonomy modules, new sensor packages, or advanced AI decision systems, then evaluate them in real conditions at a fraction of the traditional cost. This is where the open access ecosystem becomes a crucial weakness for any adversary. Legacy military jets are closed worlds, rigid and slow. Beacon is deliberately open and tech agnostic. This exposure of adversary weakness allows outside experts to plug in their tools without redesigning the aircraft. Partners like Applied Intuition integrate vehicle intelligence, AutoNodyne adds advanced unmanned autonomy, and Merlin supplies assured autonomy for safety-critical missions. Red 6 overlays augmented reality into flight environments for training. Each partner adds new capabilities that Beacon can absorb and deploy rapidly, ensuring the jet is a living platform that evolves with every integration. The very structure of this development ensures US dominance feels inevitable. Adversaries are forced into large, slow, expensive leaps, while Beacon improves continuously. The hardware supporting this dominance is the Scaled Composites Model 437, which is lightweight, adaptable, and engineered for reliability. A stable airframe keeps Beacon low risk, making it ideal for repeated testing cycles. This means autonomy software can be refined, patched, or replaced without grounding the aircraft for structural changes.
Before we get to that, I need your help. I'm trying to hit 50,000 subscribers by the end of the year, and I need your help. So I would really appreciate it if you could subscribe and help me out.
The hardware supports the software, and the software unlocks the hardware's potential. This symmetry gives Beacon unusual efficiency in real missions. At the centerpiece is its core intelligence, Prism. Prism handles high-level autonomy, mission planning, and real-time safety management. Instead of needing constant human oversight, Beacon can plan routes, manage resources, monitor risk, and adapt to surprises dynamically. As the software matures, the platform shifts from human-supervised autonomy to full mission-level autonomy. This means the jet participates in complex operations without waiting for external commands, turning milliseconds into opportunity. The stakes are rooted in the speed of innovation. Threats evolve faster than traditional programs can update. Beacon attacks this problem directly. Continuous deployment pipelines let engineers push updates rapidly. The modular ecosystem avoids the recertification bottlenecks that cripple slower programs. This brings urgency to the mission. Autonomy is no longer optional. It is required for contested airspace and missions too risky for pilots. Beacon becomes the testing ground where the next generation of autonomous behaviors is shaped and validated. A target recognition module, a collision avoidance algorithm, a swarm control interface, each is built, inserted, flown, and perfected in Beacon before being deployed across entire fleets. The aircraft becomes a confident filter that turns promising concepts into mission-ready tools. This speed of innovation is where Beacon's edge over heavier foreign fighters begins. In combat, the speed of information decides who survives, and Beacon was built for that moment. Its entire design revolves around one dominant idea: seeing first, deciding first, and acting before an opponent even understands what happened. The Prism software does not wait for a pilot to interpret sensor inputs. It instantly fuses data from radar, electro-optical systems, passive detectors, and digital threat libraries, creating a live picture of the battle space that is clearer than what many heavy manned fighters can achieve with full crews. This real-time clarity becomes a weapon. Larger foreign fighters rely on bulky systems stitched together over decades. Their processors struggle to merge data smoothly, exposing their weakness. Beacon integrates sensors inside a digital architecture designed from day one for fusion. The result is faster threat recognition and faster engagement cycles. In contested airspace, delays mean death for the adversary, and Beacon removes that delay. This dominance grows when stealth is added. Beacon's low observable shape shrinks its radar signature so drastically that many enemy sensors see only noise instead of an aircraft, a clear humiliation of the adversary's detection capabilities. But stealth is not the only key. Beacon pairs its low observable design with software that understands how it is being scanned. The autonomy engine instantly reads incoming emissions, identifies the radar type and mode, and adjusts Beacon's behavior. It shifts flight paths, reduces signature angles, and prioritizes silent sensors when needed. Heavier foreign fighters simply cannot hide so precisely. Their bulk works against them. Beacon uses smallness as a tactical asset to live inside the enemy's gaps. Autonomous flight elevates this dominance further. Prism analyzes thousands of variables at once. It recognizes enemy tactics, predicts missile trajectories, and selects optimal countermeasures automatically. A human pilot cannot process data that fast, and a heavy fighter with multiple crew cannot match this speed. Beacon turns milliseconds into opportunity. It can predict when an enemy radar will switch modes or when a missile seeker will activate, and it maneuvers preemptively. Older fighters react after the threat appears. Beacon moves before the threat materializes, relying on mathematics and training data, not fragile human interpretation. Its electromagnetic discipline is an advantage. Beacon emits less and listens more, using passive detection whenever possible. Heavy foreign fighters radiate constantly, revealing their position long before Beacon becomes detectable, exposing their lack of discipline. When Beacon does radiate, the autonomy engine shapes the signal, changing power, angle, timing, and repetition to minimize its signature trail. With large fighters, emissions reveal identity. With Beacon, emissions are puzzles the adversary cannot solve.
Before we get to that, I need your help. I'm trying to hit 50,000 subscribers by the end of the year, and I need your help. So I would really appreciate it if you could subscribe and help me out.
Survivability is reinforced by electronic deception. Beacon's autonomy controls digital emission tricks that distort targeting solutions. Where a heavy fighter requires manual input or pre-programmed tactics, Beacon invents tactics on the fly. If a radar locks, Beacon alters its profile. If a missile approaches, Beacon deceives its seeker. Autonomy makes deception fluid. The aircraft's ability to handle threat saturation is where it shows its most advanced behavior. Heavy fighters become overwhelmed when multiple systems attack at once. Beacon becomes sharper. Its software isolates the highest danger, assigns decoys, deploys jamming, and shifts position with calculated precision. The adversary's bulk becomes a liability. Beacon's size becomes its strength. The surprising truth about Beacon is its optionally manned architecture. This design is not a clever choice. It is a direct solution to a growing problem, ensuring human pilots and autonomous aircraft remain connected. Beacon can fly completely alone under advanced AI control, yet it can also take off with a human pilot in the cockpit, ready to override the system instantly. This dual nature changes how future combat will be deployed. Every failed test or crashed prototype can set programs back months. Beacon's dual mode reduces that risk while keeping innovation fast, a crucial relief loop for US development. The cockpit is a fully integrated interface that lets a human step into an AI-driven aircraft without interrupting the autonomy stack. The safety pilot can monitor decisions and override them with direct manual command. This balance builds trust, which is the real currency in autonomy development. The open access ecosystem allows multiple companies to test how their autonomy stacks behave in real flight conditions, solving the problem of different drones from different vendors that cannot communicate. Beacon gives developers a place to solve this failure of coordination before real missions demand it. Pilots want to stay relevant as AI advances. With Beacon, autonomy becomes an ally. The pilot in the cockpit observes how the AI handles tasks like navigation, threat avoidance, and formation keeping. This observation turns skepticism into confidence. Pilots become mentors, participating in the future instead of being replaced by it. This is a powerful identity, binding for the user and the Force. Beacon's architecture addresses mission flexibility. If the autonomy stack struggles due to conditions like weather or interference, a pilot takes over. If the mission requires infiltration into contested airspace, Beacon flies unmanned, removing human risk. It becomes the nerve center for manned-unmanned teaming, or MUM-T. It can act as a controller, relay node, or collaborative wingman, sharing situational awareness with multiple aircraft. Beacon solves the problem of slow testing speed. Partners upload new autonomy modules. Engineers observe the behavior in simulation and in flight. When autonomy behaves correctly, the pilot stays hands-off. When something deviates, the pilot intervenes. This creates a safe environment for aggressive experimentation. Air forces around the world are racing to build these systems. The US needs a platform that accelerates testing without sacrificing safety, and Beacon provides this acceleration, ensuring the US capability evolves at a higher rate than any rival program. The industrial tempo is where US dominance is asserted at scale. Everyone focuses on the best single fighter, but the real question is who can field the most capable aircraft? Fast, at scale, without collapsing under cost. Beacon is built as a high-rate, modular, autonomous testbed from day one, shaped by more than a mountain of 500,000 hours of autonomous flight research. Traditional manned fighters are bottlenecks. Every new upgrade requires deep structural work and painful downtime. Beacon starts from a different logic. Its open architecture allows hardware and autonomy payloads to be swapped, integrated, and validated in short loops. Sensors, mission computers, electronic warfare packages, instead of being welded into a fixed airframe, they ride on a flexible backbone built for change. Digital engineering is the silent engine behind this. Northrop uses digital models of the aircraft and its production line. Engineers run virtual builds and simulate software changes against thousands of scenarios, shrinking risk before the first physical part is made. On the factory floor, this means streamlined assembly and a predictable workflow. When autonomy code changes, workers do not rebuild the jet. They simply load new software, run validation, and push the aircraft back to the queue. Hardware stays stable, but capability evolves. This is where numerical superiority becomes realistic. Classic fighters are slow to build and slower to modify. Beacon is deliberately the opposite. It treats the airframe as a reusable carrier for evolving autonomy, not a sacred object. A single Beacon platform can be configured for sensing, jamming, strike support, or loyal wingman roles by swapping payloads and updating autonomy behaviors. This means one production line feeds many mission sets. In a contested airspace, platforms will be lost. If replacements take years, the force thins faster than industry can refill it. If Beacon airframes can be produced and upgraded in high-rate cycles, commanders can plan around surge capacity instead of hoping every expensive manned fighter survives. The psychological cost of loss drops. This frees U.S. planners to use the aggressive tactics required to saturate enemy defenses and hold airspace. Adversaries watch production signals. A country that can roll out small numbers of elite fighters sends one message. A country that can repeatedly field large numbers of capable, networked autonomous jets sends a much sharper one. Beacon's design is engineered to support this posture. High volume without hollowing out performance. Beacon's stealth lineage, inherited from decades of work on the B-2 and B-21 bombers, provides unquestionable heritage. The B-2 flying wing was chosen because it bends radar energy away from the source. No right angles, no easy corners for radar waves to grab. That experience flows straight into Beacon's airframe. Its shape, edges, inlets, and exhaust are all informed by earlier lessons in radar cross-section control, ensuring the enemy sees noise instead of an aircraft. Beacon inherits knowledge on how to cool and shield hot exhaust plumes to defeat infrared sensors, making it harder to track with heat-seeking weapons. The goal is always the same: force the enemy to see Beacon late, see it poorly, or not see it at all, thus humiliating their detection systems. Its coatings are an evolution of those used on the B-2 and B-21. Earlier, radar absorbent layers were maintenance-heavy, demanding time and money. Beacon benefits from more durable, easier-to-sustain materials, ensuring that low observability does not cripple the sortie rate. Its stealth features are integrated with its mission systems, sensors, and software from day one through shared digital models. Modularity means Beacon is not locked into a single mission set. Stealth strike today, cooperative targeting, or electronic support tomorrow. The platform can change roles while staying hard to see. Beacon does not start from zero. It enters the sky already backed by a long chain of solved problems and bitter lessons. It does not rely on a single trick. It layers radar, infrared, acoustic, and electronic discipline using shape, material, software, and tactics together. This is patient, decisive knowledge about how to disappear on radar screens, how to endure long missions without burning through fuel, and how to plug into digital battle networks without exposure. The modular design allows the U.S. Air Force to upgrade faster than any rival program. Traditional jets are locked inside proprietary systems, slowing innovation to a crawl. Beacon removes this bottleneck with a technology-agnostic architecture, allowing multiple partners to integrate at once. This isn't just collaboration, it is speed. A software change in a legacy jet can take years due to repeated certification and extensive flight validation. Beacon uses continuous integration. Engineers simulate and update digitally, stress test it in virtual environments, load it into the aircraft, and flight test it within days, not months. The result is an aircraft that evolves like software, while rival programs evolve like slow, rigid hardware. Beacon includes modular bays, modular avionics racks, and modular payload compartments that can be swapped without heavy maintenance. Technicians replace individual modules, and avionics packages can be replaced in hours instead of weeks. This means mission-specific loadouts can change faster than the tactical environment shifts. A beacon. Flying early warning missions today can be reconfigured for strike support tomorrow. This decisive speed is a survival advantage in the era of drone swarms and AI targeting. Rivals rely on modernization programs that take decades. Beacon upgrades come as software pushes, hardware swaps, and rapid cycle missions. This means the U.S. Air Force can respond to new threats before adversaries even complete the analysis of their own failures. Speed becomes the shield, and modularity becomes the sword. Falling behind is catastrophic. Beacon prevents that slowdown by design. Its open ecosystem, digital engineering, rapid iteration, and modular payloads make it the fastest upgrading platform in U.S. aviation history. The ultimate consequence is control. Beacon gives control back to decision makers by reducing uncertainty. Leaders can validate autonomous behaviors first instead of gambling on untested AI. Beacon allows developers to shape the AI's boundaries aboard an aircraft built for experimentation, reducing risk and building trust. This technology will shape the next 10 years of aviation more than any new engine or airframe. Strategically, Beacon supports a shift from a few kings of the sky to many smart pieces on the board. Air superiority is now determined by the density of capable nodes in the battle space and how fast those nodes can be regenerated when the enemy knocks them down. Beacon is explicitly built to be one of those regenerable nodes. Every time a Beacon airframe takes off with a new software load, it is a data gathering event. Lessons learned from one aircraft can be applied across the fleet without redesign. Numerical superiority is not a static count of holes on a ramp. It is the product of 3 linked curves: how fast you can build, how fast you can upgrade, and how fast you can learn. Beacon is designed to steepen all 3. Beacon is the foundation of manned-unmanned combat teams, not because it stands alone, but because it makes the entire formation stronger. It transforms chaos into clarity, confusion into awareness, and isolated aircraft into a coordinated force. Every autonomous system deployed across tomorrow's fleets will carry something learned inside Beacon. Every mission architecture tested for next-generation operations will trace part of its origin to this testbed. Beacon is not the future aircraft. It is the aircraft that builds the future. Its efficiency is in the speed it gives to the entire aviation ecosystem. Beacon, by Northrop Grumman, is the engine accelerating the next era of flight, ensuring US and Allied dominance remains inevitable for years to come. What you've seen is only the beginning. America's power is just getting started. On your screen is the next video. Click the video, it opens right away, and you'll watch US jets and technology strike even harder.